In section 1.4, we're going to review different ways of solving quadratic equations. Let's start by reviewing what a quadratic equation looks like when written in standard form. We have a times x squared plus b times x plus c equals 0, where a, b, and c are real numbers such that a is not itself equal to 0. And the reason is, if a were equal to 0, we would lose our first term, which is the quadratic term. And in essence, we would end up with a linear equation instead of a quadratic. The zeros of a quadratic function, f of x is equal to ax squared plus bx plus c, are in essence the solutions of the associated quadratic equation, where we set a times x squared plus bx plus c equal to 0. This statement is one that really just helps us understand the language of what it means to find the zero of a quadratic function. It is equivalent to solving the equation given here. Quadratic functions can have real number or imaginary number zeros, and quadratic equations can have real number or imaginary number solutions. So again, we're making a parallel between what it means to be the zero of a function and to be a solution of the corresponding equation. Two different ways of referring to the same set of numbers. Here we have the principle of zero products, which in other classes may be referred to as the zero product rule or the zero product property. It states that if two numbers a and b multiplied together give us 0 as a product, then it must be that one of the numbers was originally 0 to begin with. Equivalently, we can say that the only way to get 0 by multiplying is if we multiply by 0 somewhere along the way. We're going to use this principle or this property to solve the following two examples. We have 3x squared plus 9x is equal to 0. Notice that this is a quadratic equation written in standard form where c is equal to 0 because we don't see a constant term. I can factor the greatest common factor on the left-hand side of the equation. In this case, 3 times x would be the greatest common factor. So to factor, I would have 3x times x plus 3 equals 0. Here we have 0 by multiplication, therefore I must have multiplied by 0 somewhere along the way. I'm going to set each of the original factors equal to 0. Either 3 times x is equal to 0 or x plus 3 is equal to 0. Solving these two smaller equations yields that either x is equal to 0 or that x is equal to negative 3. That means that I have two solutions to this quadratic equation, 0 and negative 3. In my math lab, it's possible that it'll ask you to write the solution set as a set of numbers. So if you see the curly brackets like this, it might ask you to list the solutions with a comma. In a set, order is not important, and so you can write the solutions in any order. Let's look at example 2. 3x squared plus 7x minus 6 is equal to 0. Here factoring is a little trickier, and we may have to use a little bit of trial and error. On the left-hand side, we'll attempt to factor the quantity 3x squared plus 7x minus 6. There's really only one way to factor a 3x squared. We'll write it as 3x times x. But there are several ways to factor a negative 6. For example, we can write negative 6 as positive 3 times negative 2, or positive 6 times negative 1, or maybe those same factors but with opposite signs. We want to factor it in such a way that we get the correct middle term when we multiply the factors that we come up with. With a little bit of trial and error, we might find that the correct way to factor the negative 6 is to use a negative 2 first and a positive 3 second. Off to the side, I'm going to show you why this works, although with practice, you should be able to check your factoring very quickly. let's go ahead and multiply 3x minus 2 by x plus 3 by distributing, and let's just verify that we get back to 3x squared plus 7x minus 6. Again, distributing using the FOIL acronym, first times first gives us 3x squared, out times out gives us a positive 9x, in times in gives us a negative 2x, and last times last gives us a negative 6. By combining the two middle terms as like terms, we confirm that we do indeed end up with the original trinomial. Now that we have confirmed that we have factored properly, we are going to apply the zero product rule and state that either 3x minus 2 must equal 0 or that x plus 3 must equal 0. Solving the first equation gives us that 3x is equal to 2 or that x is equal to 2/3. Solving the second equation gives us that x is equal to negative 3. So we have two solutions to this quadratic equation, and again, we can write the solutions in any order if we are using the set format. The second method for solving quadratic equations is using the principle of square roots, which says that for any real number k, if x squared is equal to k, then x is equal to either the principal square root of k or the negative square root of k. Notice that k just has to be real. It doesn't even have to be positive. So this also will yield some roots that involve imaginary units. Let's take a look at the two examples below. We have that x squared plus 25 is equal to 0. This quadratic equation is written in standard form, but unfortunately, x squared plus 25 is not factorable. This is a prime binomial. So our first method of using factoring is not going to be an option. Instead, let's rewrite this equation as x squared is equal to negative 25. Negative 25 is a real number, and because we now know that complex numbers follow rules that real numbers do not, we can apply this principle of square roots to say that x is equal to either the principal or the negative square root of negative 25. Well, the square root of negative 25 can be written as 5 times I. So there are two solutions here. X is either equal to 5i or x is equal to negative 5i. We can use this plus or minus symbol when my math lab allows us to, but another way of writing the solution is to list the two solutions separately in set notation as negative 5i and positive 5i. In the second example, we have x minus 7 quantity squared minus 16 is equal to 0. It looks like we already have the left-hand side factored, but we really don't, because we have a little bit of distributing and collecting of like terms that would have to happen first. However, I can add 16 to both sides to write this as x minus 7 quantity squared is equal to positive 16. Here, 16 is acting like k, and x minus 7 is a unit that is being squared, so I can apply this principle of square roots. I can say that x minus 7 must equal the principal or the negative square root of 16. This time, the square root of 16 simplifies beautifully to just 4. So that means that x minus 7 is either equal to plus or minus 4. We want to isolate x, and so we're going to add 7 to both sides of this equation. We have x is equal to 7 plus or minus 4. This gives us two solutions. Either x is equal to 7 minus 4, which is 3, or x is equal to 7 plus 4, which is 11. So we have two solutions to this quadratic equation. The two solutions are either positive 3 or positive 11. Our third method for solving quadratic equations is to use a method called completing the square. Completing the square does involve quite a bit of steps, and so let's review how to use this as a method. The good thing about completing the square is that it is always an option when solving a quadratic equation. We don't have to have anything that's factorable, and we don't have to have any perfect squares because we are going to create a perfect square. Review these steps on your own, and we will model them in the following example. We have x squared plus 6x minus 6 is equal to 0. Notice that this trinomial is not factorable, so we can't use the factoring method. It's also not a perfect square, and so the principle of square roots will not apply either. However, we're going to use the completing the square method. The first step is to make sure that we have the equation written in standard form, and we want to have the leading coefficient to be a positive 1. Notice that the leading coefficient here is implied to be a positive 1, and so we're good to go. If it wasn't, then the appropriate first step would be to divide the two sides of the equation by that leading coefficient. So in essence, we're forcing the leading coefficient to become 1. The next step is we're going to move this constant term to the right-hand side of the equation. So we're going to add 6 to both sides. We have x squared plus 6 times x equals positive 6. You may note that I left some room here on the left-hand side because we are going to add a real number that is going to create a perfect square on the left-hand side of the equation. Of course, because we have to keep the two sides of the equation balanced, whatever we add to the left, we will have to also add to the right. To find out what number to add to create a perfect square, we are going to take half of the middle coefficient. So in this case, we're going to take half of 6, and then we're going to square that. So half of 6 is 3, and then we're going to square the 3 to get 9. That is what we're going to add to the two sides of the equation. So we're going to add 9 to the left, and we're going to add 9 to the right. The reason we did this is that now the trinomial x squared plus 6x plus 9 can be written as a perfect square. In fact, this is equal to x plus 3 quantity squared. You can verify this by distributing out the multiplication x plus 3 times x plus 3. On the right-hand side, we have 15. Now we have a perfect square on the left and we have a real number on the right. We can use the principle of square roots to say that x plus 3 is equal to the principal or the negative square root of 15. 15 is not a perfect square, and it does not contain any perfect square factors other than 1, so that is as simplified as we're going to be able to express that quantity. To isolate x, we can subtract 3 from both sides of the equation to get that x is equal to negative 3 plus or minus the square root of 15. Again, we can write the two equations in this compact form, or we can write the two solutions separately. X is either equal to negative 3 minus the square root of 15, or x is equal to negative 3 plus the square root of 15. So we have two solutions to this quadratic equation, and we can write them in set notation by separating them with a comma. Finally, the fourth method for solving a quadratic equation is the quadratic formula. The quadratic formula, in essence, completes the square for us. It's built in to the formula itself. You do need to know the quadratic formula by heart. There's lots of different ways for you to use mnemonic devices to remember the formula, but whatever it takes, make sure that you know it by heart and that you can replicate it without errors. The beauty of the quadratic formula is that it can be used for any quadratic equation. If you have a trinomial that's not factorable, that's okay. You can use the quadratic formula. If you don't have a perfect square scenario and you don't want to go through the process of completing the square, you can use the quadratic formula as well. So there is no quadratic equation for which this is not an option. We do need to have the quadratic equation written in standard form. So we see here in the example, we have 4x squared minus x is equal to negative 7. we want to make sure that right-hand side is set to equal to 0. So the first thing we're going to do is we're going to rewrite this as 4x squared minus x plus 7 equals 0. Carefully, let's identify what a, b, and c stand for. A here is equal to 4. B here is equal to the coefficient of x, which is -1. And c here is equal to +7. So using the quadratic formula, we're going to substitute these three real numbers very carefully. In this case, we have x is equal to the opposite of b plus or minus the square root of b, quantity squared, always make sure you put b in parentheses, minus 4 times a times c. All of that will be divided by 2 times a. Really important that you're careful with your negative signs and that you use parentheses when you are multiplying and squaring. Now let's simplify carefully. The opposite of -1 is 1. -1 when squared is a 1. 4 times 4 times 7 is, I'm going to have to do that off to the side. 17 times 7, so that is 2.4, 112. So 1 minus 112 will give us -111 as the quantity under the radical sign. In the denominator, 2 times 4 is 8. Now 111 is a prime number, so we're not going to be able to simplify the square root of 111, but we do have that negative sign as part of the radicand. So we can do one more thing to simplify this answer, and let's write this as 1 plus or minus I times the square root of 111, all divided by 8. Again, these are two separate solutions. The solution set includes the quantity 1 minus I times the square root of 111 all over 8, and 1 plus I times the square root of 111 all over 8. The last part of our discussion here in this section is to talk about the discriminant. The discriminant is that quantity underneath the radical symbol, b squared minus 4 times a times c. When the discriminant is equal to 0, we will end up with only one real number solution to our quadratic equation. When the discriminant is positive, we'll end up with two different real number solutions. And when the discriminant is negative, as it was in this example, we end up with two different imaginary number solutions. And it will always be the case that they will be complex conjugates, as we saw in the example above. Using the discriminant alone, we can predict how many solutions there will be to a quadratic equation without having to solve entirely. For example, 4x squared plus the square root of 3 times x plus 8 is equal to 0. Here we have that a is equal to +4, b is equal to the square root of 3, and c is equal to +8. By calculating the discriminant, we can determine how many solutions we will have and of what type. In this case, b quantity squared is the square root of 3 quantity squared minus 4 times 4 times 8. This simplifies to 3 minus, oh boy, that's a big number. Is it 128? Let's see, 16 times 8. So that's 16 times 8. I can't even multiply correctly. Let's see, 6 times 8 is 48. And yep, that looks good, 128. So we get -125. Because we have a negative discriminant, we know that this quadratic solution is going to have two complex number conjugates.